Hello, everyone. I hope I let you be awake here. So today, my talk, our discussion is about our journey of advancing the virtio specification for live migration functionality. Before I jump into it, I'll give a short introduction of what it is about. Virtio is another open community which drives the various types of devices. There are 19 at least different device types of virtio. The most common is networking, block, file system, console. This is what I could recall, but there are other 19 different types. Um, Spans from data center for these three types to automotive, including sound and other devices. So um, our work, what I'm presenting here is a work of several people who contributed to this, and I'm just presenting it. Um, um, so we advanced the virtio specification to support the live migration of virtio PCI devices. PCI, fundamentally PCI virtual functions, which are implemented in hardware. And I think I'm going to run over my time, so I don't want to miss acknowledging them. So I would first acknowledge um, several people's work who contributed here. Michael Tiskin from Red Hat largely contributed in simplifying and extend and doing the design that is extensible. Jason Wang from Red Hat also helped us to get several of the synchronization pieces between the driver, hypervisor, and the device tied up together. CV from Oracle, who we just listened to, he presented the idea of a device state migration back in 2021, I think, in the KVM forum. So we learned a lot of those ideas from his work. Um, Several other people gave their comments, including Jason, Max, Gal Shalom, Tanya, and Ben Walker from NVIDIA, who helped to review the design and solidify several aspects of it. Who also work with several other communities, including NVMe and others, to make our design more solid. With that, this is the joint work that I'm presenting with Marvell, NVIDIA, um, and a couple of contributors from Red Hat. Okay, so now come to the technical part. So this is 10 slide, but it's an overview, a good start to understand. On the leftmost is the pure software implementation of a virtio device, where there is a hypervisor, Linux kernel, and on the top we have a guest VM, which sees a virtio PCI device. Who composes the virtio PCI device? The QEMU hypervisor composes the full PCI device, including config space, doorbells, ring areas, which connects to the vHostnet backend in the guest in the QEMU, and that connects to the Linux kernel. And all the transmit receive of the packet happens through the non-virtio NIC. Baseline working for several years. Here we characterize based on the three things when we compare the solutions. One is the user API. What's the user API between the QEMU and the Linux kernel? So here it's vHostnet API. Second characteristic we do is performance. What's the performance do we get? The performance that we get is CPU bound essentially in the hypervisor, because that's the one that's converting every single virtio transmit and receive packets into a hardware packet. And the third one we characterize is migration. How long do we take to migrate? And what's the cost of a migration? And the cost is not just um, downtime. The cost of maintaining the code, cost of upgrading the software, cost of adding, removing new features, cost of provisioning, and the final cost of the downtime, that what ultimately matters. So these are the three parameters that we characterize on. Second method is what we already see in the last presentation of VDPA, where you have a vendor-specific driver running in the hypervisor that is exposed through a VDPA bus driver. On top of that, a vhost VDPA driver. and then there's the user space component of vhost VDPA, and we still have a QEMU who composes the PCI device. So there are 5 software layers that interacts with each other to actually make a virtio PCI device in the guest VM. Here there is a VDPA device. So VDPA is the data path acceleration. P stands for vhost or virtio. I'm not sure. What do we get here? We get here is a better data path performance. User API is vhost VDPA, and there is some amount of saving on the hypervisor because now all the data path is running in the hardware for transmit and receive. And migration here is several costs involved of the user space, vendor driver, QEMU, and kernel modules. What we saw in our previous presentation. And the third one is all about today's talk. The third method, which is on the rightmost, what we see is there is a virtio PCI NIC, a NIC that you can touch and feel, remove from the system and insert. That's the green box, which is a PCI NIC that has a virtual function connected in Linux kernel using a VFIO virtio PCI driver, one module, and it connects to the QEMU VFIO PCI. And here what you see is a single driver or largely a single subsystem that would work for all type of devices. Because the user API here is an abstract user API between the QEMU and Linux kernel is a VFIO. What's the performance to expect? Performance is the hardware because all the features, all the functionalities of the data and control plane is in the hardware. And the migration performance, the cost, migration cost is only VFIO kernel module and the VFIO user space component for it. So what are our goals? Goals that we started with in our journey was mainly 4 goals. First, we want to achieve a device downtime, which is less than 200 milliseconds. We want to make this work for an actual PCI devices implemented in hardware. The 200 millisecond downtime that we want to achieve was for number of devices, being it a 1 device in a VM or 4 or 8, for a large memory of 128 gigabytes per VM, and for CPU scale all the way up to 64 or 128. Third goal that we had is we wanted a single data path for migration framework. Data path here is not really a data path, but it's the migration data path. And the fourth one is in recent time we see that the virtio is going through several upgrades of the new features. So when we add new feature, do not want to constantly touch the hypervisor or rest of the other system. To add new feature, we don't want to touch the migration driver. If I take a Linux driver example, it has close to 300,000 lines of code. And if that would have taken an approach to have the control plane in the migration driver, probably an impossible task for Saeed or anybody else to maintain that kind of a migration driver. The migration driver for Linux device is close to 15,000 lines of code, all put together. So we started with that as a baseline. And with that baseline, we came up with the 10 design principles. What is it that we want to achieve in our design? So I'll probably spend slightly more time on walking through the design principles rather than going bits and pieces of the callback functions or NDO operations kind of work. So the 10 principles that we started with is we want to have O1 downtime regardless of number of devices that we attach to a VM. Because when you deal with hardware, every hardware access or operation that we do is going to take a finite amount of time. And we add more device, more queues, downtime should remain nearly constant within our budget of 200 to 400 milliseconds. The 101 that Dragos mentioned is we want to have least number of operations in the VM downtime. Every operation that we do costs something. So let's design an interface between driver and device for the migration to do as minimum operations as possible while the VM is down. It can do more operations while the VM is running. That's fine because that doesn't cost much towards the VM downtime. We also need to support a device reset. Whatever device reset can be done by the whatever driver itself or a FLR that can be issued function level reset by the guest driver. So while the VM is getting migrated, these operations can be done. And the migration driver should be agnostic of it. At the same time, the state migration needs to understand these nuances. So we need to support that. The design that we work needs to work with SRIOV VM as well as the SIOV R2 devices, which are upcoming in the industry probably by this year end. So we want to have the least amount of changes between these two scalable functions as well as the VS. Number 7 is, like I mentioned, we want to have a same user API between the user space and the kernel, regardless of the device type, being NVMe, Mellanox, virtio, or any other device type. PCI peer-to-peer support. Even though virtio is probably not that at current level in serving the performance, but a VFIO community, a VFIO subsystem took a stand saying if you want to support a VFIO-based live migration, the device bare minimal watermark it needs to reach is to support peer-to-peer. So that as a baseline was our design consideration. And that has a key area on how the device is being suspended or resumed has those touch points. We want to utilize the dirty page tracking. Like CV mentioned in previous talk, dirty page tracking is there in the CPUs of Intel, AMD, and in the ARM specification, IMMU. And with recent CPUs, we see that it's supported. So wherever it's there, we want to use it and make that part optional for the virtio spec. And the last one that we want to consider here is any migration driver that we do. Essentially, it's going to sit either in hypervisor or some trusted VM. Consider the confidential compute on the horizon. So we want to support all the three, ID, TDISP, and confidential compute semantics going forward with the live migration framework that we do. So with these 10 principles, the design became kind of obvious, saying, yes, this is the path to go. Like Andrew mentioned, we want to learn from the good drivers present in the Linux kernel. So a VFIO was an obvious choice for us to achieve that. So what we have is a zoom out version of VFIO PF. There are many virtio VF virtual function devices. These are the pass-through devices to the QEMU and guest VM. And a virtio PF serves the migration channel. So VFIO driver has got two kind of bifurcation in it. One is the migration commands and one is the actual VF commands. This has been a classic Linux kernel model for several drivers that exist. Now, obvious question is why PF? If you go back to our design principles, you will learn that we want to support FLR, we want to support function level reset, and the whatever device level reset. And since those are happening on the VF, a migration channel cannot be on the VF because those two operations, somewhere or the other, is going to block it. So that's why the trusted PF is in place to handle this migration. Second need of the migration interface is there can be many VFs whose migration can happen. It means that we need to do data transfer asynchronously between the driver and device. That means we need an admin queue or some sort of a queuing interface between the two. The device state transfer will also require DMA. The moment we do AMA, it cannot be a small config registers that you can do in and out on the PF or a VF. This is the one that makes it energy efficient, because when we scale to 2000 virtual machines, we're going to have 4000 VFs attached to it, either of virtio or various different types. This is why we want to have a queuing interface there. That's pretty much it. I want to zoom in now. If we zoom in, what we see is config channel, a control channel between the drivers. So this is the spec or the setup that we have, for which we derive the performance numbers. On the rightmost, what we see is the virtio net PCI device passed through in the guest, applied through using a VFIO virtio VF driver that connects to the PCI driver. You notice the virtio PCI driver of the PF is serving two channels. Number one, it's serving all the commands that are coming through the VFIO side. At the same time, it's serving the virtio net device as well. It is used for migrating the data from one to the second hypervisor. One driver using the two sub-channels. We are not using any auxiliary device in the Linux kernel yet, but it kind of serves the purpose right now. And on the leftmost, what you see is an IOMMU FD, which CV mentioned in his previous talk. We use the IOMMU FD to do a dirty page tracking. This is using the CPU AMD Innova as well as Intel Sapphire Rapids. Both the CPU platform supports the dirty page tracking. So we use the most recent 6.8 kernel's API and the CPU work to perform the dirty page tracking. And that essentially keeps the virtio migration design quite simple. So the two things to notice and take away is between the user space and the kernel, the common UAPI is VFIO, is not virtio API. Second takeaway is for IOMMU tracking, also neutral UAPI across all CPUs with the IOMMU FD. There is nothing vendor specific done here between these two. Okay, with that we come to the second part of the design. So what exactly is done in the virtio specification to fit this software model? We divided into three kind of commands. It's very simple. First one is the device mode handling. Whenever you want to suspend or resume a VM, you suspend vCPUs, you stop working them. At the same time, you need something on the device side saying, you got to stop working because I want to suspend you. If I can suspend you as a migration or a hypervisor driver, then I have a way to get your state and all the data I can transfer to the other side. So there are two simple commands, stop and resume. And when it is stopped, you can still have a peer-to-peer device talking to you, pressing the doorbell. So the virtio specification included this part saying even though the device is stopped, it should expect a doorbells coming in. They are called kicks or they are called device notifications. So the meaning of the stop is not really a stop, but it is stop to access all the memory of the guest VM, but it can still expect the kicks coming from the other peer-to-peer PCI device. This was the simple one command. Then we had a bigger challenge of saying, okay, the virtio device of the PCI NIC is implemented by many hardware vendors. How do we implement those part of the vendor blob of the device state? So we came up with a device parts as an abstract concept, which is derived very much from the netlink TLVs, where every netlink message can have a type length and value. So our device parts are of virtio are following just TLV format, where every is defined as can be migrated in the source hypervisor, and there can be several of these device parts. Which device parts exist for which device is chosen by the cloud operator, because cloud operator is the one who is deploying this device in their cloud. So they pick and choose what parts they want to transfer. Of course, it's mandated by the virtio spec of what orders it should go in, so that you can't miss. A vendor who is implementing the virtio device cannot miss any of these parts. Device parts are split into two. One is the common. If you recall, there are 19 different virtio devices. So we split these device parts into two large categories. One is common and one is device specific. Common is something that nobody needs to implement again, other than those 19 types. So all 19 types share these common device parts because they are literally common across all types. And then you have a device specific parts. For example, a virtio net device would have an RSS context, RSS queue context, number of channels that is being used. Those are the parts of the net device context, or several MAC addresses or a VLAN table that's been configured by the guest driver. That's the net specific part. And this is agnostic of any generation. We do not have versions in our device part context, because every part represents itself. The moment we have version, it tends to break, because you get into a complexity of which version does it support and which doesn't. And the last part of the device part is it's all wrapped into something called device resource objects. So resource objects is a generic concept that came from REST APIs or CRUD, create, read, update, destroy. So we bring in this concept into virtio spec as a resource object that you can create, modify, read, or destroy. When you create, it gives the enough hints to the device saying, look, I as a migration driver, I'm going to read some of the device state or the device parts that you have. So prepare yourself to bring it from your flow portion into the memory. For example, many of the flow steering rules would not be stored in the memory. They can be part of a TCAM or other areas. And it might be very slow to bring them in. So resource objects are providing enough hints for hardware to bring them in, which is on the read side. Same happens on the writer side, on the destination hypervisor, where we create the resource object of saying write type. I'm going to migration driver. I'm going to write these device parts. Prepare yourself and store these device parts as you need it. That defines the second part of our device part. The third is saying, okay, I defined the device parts, but how do I access it, the migration driver? So we define three simple commands: get parts, set parts, and metadata. I'm going to skip the metadata for now because I probably will run out of time. We can come back if the time exists. So get and set is a simple command. You can set one or multiple parts using this command. If we see on the right side saying, okay, I get these three building blocks of my Lego. How do I achieve the live migration? So I jump to I skip the basic migration part and jump to the pre-copy part. The basic migration is you have a VM running for 10 hours. You would stop the VM, read all the device state, go to the destination, program all the device parts, and resume it. This is a very simple 4-step sequence. From that sequence is not helping us to get to the downtime of the device, the VM downtime, because we want to reach into our 200 milliseconds. So we use the VFIO driver frameworks, a pre-copy method. Pre-copy, the 4-step gets into 5. First, we stop the destination side device where it is identified saying, okay, I'm going to migrate on this server. Let me pick my VF device, which is stopped. Then on the source hypervisor, we get all the device parts, get it for the first time, and we use all the techniques that already exist for the memory pre-copy, where memory pre-copy happens several times while the VM is still running. So we do exactly the same. The device parts are represented as a memory, and we migrate those device parts iteratively few times. Iterating and migrating them is not enough because the destination also needs to set those device parts in the device so that when you press a resume button, most of the things are in place. Destination side sets this device parts and acknowledges back to the source saying, you asked me to set it, I have done the job. Step 2 and 3 happens on several iterations. And at one point, the QEMU decides saying the amount of dirty memory that I have is pretty less. We miss the part to understand from the virtio spec side saying how much of the device parts are dirty. So we skip that part in our first version because really the first version we want to get it in a good shape without doing too much of over engineering. So we are missing the dirty tracking on the device on the source side. But even with that, we achieve good performance numbers that we will see in few minutes. All right. So with these three steps, the fourth step that we do, which is where the downtime kicks in. The fourth step is stop the hypervisor VM and get the final device parts. So if you observe, there are two operations, 4.1 and 4.2. Stopping the device, get the device parts. And on the destination, we set the device parts finally. 5.1. 5.2 is finally resume the device. So if you remember the design principles, we want the least operations. So here are the only 4 operations that we do during the downtime. 4.1.2 and 5.1.2. Suspend, get device parts, and exactly the reverse sequence. Get and set and resume at the last. This is a zoom in version. I'm going to skip it right now, but it's there in the paper as well that we wrote along with it. And go in details as you need. But the summary of this is that the part that contributes towards the downtime is what CV already covered in his present talk is setting up the device, its use, configuration takes time. And we want to take away that time from the migration downtime to something in the pre-copy phase. And that really helps to reduce the downtime. That brings to the interesting chart. So this is the performance chart for downtime of a virtio device, virtio PCI NIC with and without pre-copy. The configuration is we tested on both Genova as well as SPR. This particular graph is on the Intel SPR platform with the latest QEMU. We took a 6.8 kernel version and developed the VFIO driver. And we took Oracle Linux 8.4. And we did a micro benchmark with HyperV 3. Keep in mind, we still don't use the page pool in virtio net driver. Numbers are without page pool. And we took virtio Bluefield 3 DPU as our NIC, virtio NIC. So what do we see? The green graphs are the downtime with the pre-copy enabled, and the orange one is pre-copy disabled. So I'll focus on few. The first one, number 1 to 12 are written right? First one is a downtime of 128 milliseconds with one device. And the queue count is 2 there. So we took 2 devices with 2 queues. And because of the pre-copy, we reduced the downtime from 439 milliseconds to 128. Not so impressive, 300% gain for 2 queues. But the real gain is on the rightmost side of the graph, the 12th one. The 12th one has 4 devices. Each device is with 32 queues. And the VM is with the highest amount of memory of 128 gig with 32 or 64 vCPUs. There, the device downtime is from 1700, which is 1.7 seconds. We bring it down to 334 milliseconds. So we didn't achieve one here, but we are close to the O1 um, target that we want from 128 to 334, where from 2 queues we scale up to 32 into 428 or more queues. This is just the first version with pre-copy, where we did the deduplication of the device state on the destination. So if the device state is set multiple times, in most cases, it's going to be the same content. What would change between the two device states is only the queue indexes, where the producer and consumer indexes are going to change. That's pretty much the change happens. RSS table, queues, they are not changing. It's very easy for us to do a pre-copy by deduplicating the data on the destination. The second thing that we observe in our test that we used, if you remember, we used IMMU FD. So even though we use IMMU FD from first second, there is nearly no performance loss because the dirty tracking is done by the IMMU. So the IMMU FD does the dirty tracking on every single page in the system, and there also we don't observe any performance loss because of it. So that kind of gives us a good hint that what our spec is good enough start for at least the new generation CPUs. Okay, the two summary that I have is the VM downtime is a function of IO commands latency. So what we observe between these two, the red and the green, is the IO commands to suspend, resume the device, and to set up the device is the costliest time, the time that we spend in setting up on the destination as well as on the source. So this is why the pre-copy method, which is largely done for the memory-based device, is sort of helping here as well to achieve the same downtime goal. The third parameter that we observe is okay, we reduce the VM downtime, but how does that affect the total VM migration time? So what we observe is the VM migration time increases with the pre-copy method. The increased time is in the, so if you look at the last one, the 12th column, is with 128 GB of memory and 64 vCPUs. The time taken to migrate that is significantly more than without the pre-copy, with the pre-copy method. So the pre-copy does it iteratively many times. So the time to transfer the memory takes longer, and it's also a function of the vCPU. You see the column 10 and 12 has the same number of device configurations, but the memory and vCPU configuration is different. It's kind of a hint for us to indicate what's its function of. So though the VM migration time is not so important, but it gives us good insight of which component contributes towards the migration time. Is the device or it's the rest of the subsystem? With that, it brings to the last part of the VFIO state machine. Some of you are familiar with it. To see what can be further improved than our first version. So the two numbers that these two tables are indicative of the downtime breakup thing, which operation takes how much time. So this is when the VM is down, where do we spend most of our time? So when pre-copy is disabled, I'm trying to get a pointer. When the pre-copy is disabled, we spend 230 milliseconds in reading the system RAM on the source side, which is the third row on the left side. On the right side, we take only 135 milliseconds while we are reading the system RAM. Why? because the P is transferring this memory several times. So when the VM is actually down, the amount of memory that is being dirtied is pretty less. So that's why the downtime has a significant impact of at least 50% saving of reading just the RAM. The next row is also equally interesting. On the left, what we see is after 230, we spent 20 milliseconds to read the device state. You remember we had a 4-step operation. Stop the device, read the device state, set the device state, and resume. Yeah. So this is the second operation. We took 20 milliseconds to read the device state. That time, when we read the device state, when the device is stopped, is 12 microseconds. Why? Because the VFIO system knows that when the device is stopped, there is going to be a new read coming in. Somebody is going to read it, device state, because it is stopped. So we overlap the time between reading the memory and the IO operation towards the device. So the step 3 of 135 milliseconds is spent towards reading the system RAM. At the same time, the device is reading the device state from itself, because the driver knows that I can overlap my memory read within IO. That helps us to finish that operation in 12 microseconds because it never goes to the device. That operation, when it actually comes as the ioctl from the VFIO, that IO is already finished before one of the previous operations. So overlapping the compute with an IO that we used here. The next one that can be improved is a 11 millisecond. All the VFIO APIs are synchronous. They are not parallelized for 4 or multiple devices. So currently we spend 11 milliseconds to set up a device. That can be further improved if we parallelize it, nearly bring it down to 1/4 of the cost. This is largely the performance summary that would complete the picture. With that, I like to summarize for 3 minutes. I'd like to summarize and complete what we talked so far. In our design, we largely use the VFIO APIs as vendor neutral or device agnostic user API for all 19 device types across all types of device, virtio versus non-virtio. Simplified design. We started with a dirty page tracking or dirty device state tracking on the source side. Instead, we simplified with Michael's input to just do the efficient deduplication on the destination. That itself gives us 3x gain of reducing the device downtime. Fourth one is we overlap the compute and IO while the VM is down, and that helps us to gain the needed downtime needed. We can further make it asynchronous and parallel. That would be the next step, is software change, virtio spec change. The method that we did, I did not touch on the metadata part, but the whole method is transparent and managed by the hypervisor. So hypervisor has a full control and visibility into all the device parts that is being tracked. There also has an option to not track it. So if the hypervisor migration driver chooses saying, I would like to omit these 10 device parts of the state and just perform rest of the operations, then it can also do that. So the design considers that. And the device state definition finally is agnostic of any device providers, especially a vendor who implements the word NIC themselves. It's agnostic of all those hardware vendors. Specification wise, this is approved by the OSS technical committee and the community who works on it. We are expecting a couple of patches fixes in this area, and also improve the new TLVs to define the state for RSS, queue configuration, and more. So change as we improve the VirtIO spec, the only thing that we need to change is define the new TLVs. That's it. The whole framework work with the existing, new, and all the old features of VirtIO spec. Finally, the upstream driver is work in progress. We would like to extend the current VFIO VirtIO driver to support this new component. That's about it for today. Questions? Yeah.
Yeah, really good work. Thank you. There were a couple of things. One was on the design principle slide, if you can go. The first line, 0 lines of code change on hypervisor driver to add a new VirtIO feature. I didn't quite understand what you mean by that.
For example, we are adding a flow steering. VirtIO committee added flow steering to VirtIO spec, where each tool steering or ARFS can be supported as 2 use cases. Now, if a VirtIO PCI device has those 2 features, if I want to support, what changes do I need to make in hypervisor driver in the migration? This is for the, yes, live migration. So not for the guest VM. The most focus is on the, yes, migration driver.
One more comment. So do you guys also looking into post copy space? Not yet. The queue state last stop. I think you can further optimize. I think you do queue configuration in downtime. You can do it earlier in most devices, and you just can update the queue state. Don't remember the slide, but maybe a couple more back. All right, here. Yeah, so set up queues and that part, I think it can be further optimized to do it not in down.
I think this slide was comparing the how does the VDPA achieves the downtime? What are the operations in the VDPA in doing the while the VM is down, and what are the operations on the VirtIO? So left side is for the VirtIO, where 3 and 4 is what we spend. And what we see on the kernel VDPA is on the source hypervisor, there is a reconfiguration. If you remember Dragos, he showed there were 2, the VM was down twice on the VDPA. First, it was down to reconfigure the queues, configures the ASID, shifts to the shadow word queue. Then the VM operation starts running while the hypervisor is tracking. And then eventually the second part kicks in. So the 1.2 is VDPA's reconfiguration. Only the queue parts. Right.
Great work and nice presentation.
Thanks.
I'm curious, what is the prior state of the art for VirtIO live migration?
I think this is the first attempt to.
So before this, we are not able to migrate full machines with VirtIO devices?
With VirtIO PCI hardware devices, no. At least I'm not aware of. It didn't exist in the VirtIO spec. So what I'm presenting here is a work of 2 work. One is VirtIO specification development, and one is a driver development for that spec, which is under development. So it's joining the 2 work. I think there was a 2019 keynote from Ms. Alisa Cooper. He presented the TLS work of IETF of how the spec development for TLS 1.3 happened with IETF development. So it's kind of learned from her concept, saying both needs to happen in tandem, spec development as well as actual implementation development, and you learn from each other, think what is good, what is not good, and apply. So this is the first concept that we think for virtio PCI devices.
So your design is kind of comprehensive that covers all of the things. As you mentioned, like all of the 19 virtual devices.
Yes, the TLV parts are the one that would change across the device. I think the file system devices are relatively more complex. We haven't looked into it, but there were comments on the community saying very hard to migrate FS. So maybe nobody implements FS as a migratable device. Maybe it would improve.
All right. One more question, and then we have to wrap this up.
You had mentioned in the abstract something about IDPF, so I just wanted to know what that was.
So I think I was asked saying what are the differences with yours and IDPF presentation of last year. I'm not too familiar with IDPF. I see two differences with IDPF. One is we bring the first time the performance numbers, which was not there in the IDPF last time. Probably it was early in the phase. Second is we have wrapped around the device parts as a standard TLVs and the resource objects. I'm not sure how is it done in IDPF. And I'll finish the third part and give. The third part is we use the IMMU FD and use the CPU IMMU to do the dirty tracking. I think IDPF achieved it by having those commands within the device. So I think it's inevitable for virtio spec as well. But I would let time test it, saying how long do we really need it and wait for it?